Uh,
Okay.
we can do
Okay. Sorry for the hiccup. But I think it connects well to this image here. This is an image of a chemist, and this chemist gave us sweeteners. And I think the way that he gave us those sweeteners is very interesting. Because the way he found sweeteners is that he went for lunch break, and for some reason his lunch tasted sweet. So he licked his fingers then, and they were sweet, and he went back to the lab, licked the reagents and vessels, and then in this way he found sweeteners. And I think we shouldn't just rely on unsafe lab practices or luck to discover new compounds, but have a more guided fashion. But in the end, chemistry is still, at least in my impression, very artisanal. So I think this discovery process that you depend a lot on like just randomness and coincidence and like small details is still very common in chemistry. So that the context, the way you run a reaction is very important. And in the end, this is the reason we often, I think, use text to record data in chemistry because text is very flexible. You can in there record the order in which you run a reaction, the way you add stuff, the way you stir and shake, very flexibly, which is often much harder to do in a table. And so this, I think, also explains why if we now look at how much data we have in papers compared to how much data we have in data in Zenodo or structured forms, it's just on a different scale. So here we plot the number of papers we have for different fields. And you see, you have like almost a factor of 100 different data on Zenodo. So using text seems important because it's like context rich. And also we have just way more text out there in chemistry. And I think also if you think about it just for the thing we often want to do, it's very natural to think about text. Because if I want to predict a recipe, so if I'm in the kitchen, I want to predict how to make pancakes, I could of course try to make a table like this with all the ingredients, the timings, and the ratings, and try to correlate those columns of ingredients here to the ratings. But of course, you miss in this way all the nuance, like all the different steps that you in between, and thus we now do way more things with text also for recipes. And the vision of what we do in my group is to basically apply some of those ideas that we have a lot of context in text and directly enabling the end-to-end modeling between the texts of our recipes and then what we measure. Because we say that this first part here is actionable, you act upon it, you run the recipe in a lab, and all this last part here is actionable. But the stuff in the middle here is often nothing you really directly operate on. You don't change atom by atom, but you change how you create your molecule. And thus, we want to learn how to make this link between recipes and directly our outputs, and in some way skip the molecules or skip the materials because often we don't really know if we have defects in there or solid effects. And for this reason, we care a lot about using LLMs because LLMs allow us to use this data here way more effectively. And I think, at least in my point of view, for LLMs, we have many different ways of using them. We can, of course, use them to just predict things. We can use them as kind of a knowledge base we can query. We can use them to direct different tools, kind of as an agent, but also then to get new data for us into some structured form to mine data from papers and then obtain databases from it. I want to start with the first theme here, which was to predict things with those language models. And this is work we've been started with Berend, who will speak later, and Philip. And the idea here was perhaps quite naive, but it was also before the boom somehow started with those models. And the idea was that if we now have a table of materials and their properties, like if a certain alloy forms one phase or more than one phase, we would like to classify those systems into forming either single phase or multiple phase. And what we can then do in principles, we can then form question and answer pairs. So we can convert this table here into a table of Q&A. So we have the questions, the prompts, and then the answers. And then the main trick we then applied here was to fine tune a big LLM. So we fine tune, we update the weights of this model a bit to make it better at answering this question. We optimize now this LLM to be better at answering those questions here with the right answer. And we just convert now the different classes into zeros and ones to make it easier for the parsing. And we also have additional tokens here to, again, simplify the parsing in the end. But importantly, we then have the model can answer those questions more reliably. So we have a new LLM with new weights and can then ask new questions. And we can then test it how well it performs on those new questions. And this is shown here where we have a so-called learning curve. So we show how the performance of this model changes with more training points. So we start with 10 points here, go to 200 points here, and then show in this curve different models. So we have in dashed line a baseline built by domain experts, so they really know what they're doing. In contrast to me, they know how to basically build an optimized model with the optimized features for the system. And then we have some other baselines like AutoML from the Berkeley team, and also an optimized transformer from Taylor Sparks, who will also speak, I think, in this webinar series. And then we have here in blue our approach, just fine-tuning an LLM by now standards, an old LLM GPT-3, and we can beat this domain expert baseline trained on thousands of points with just 50 points. And this was quite surprising to us. You can beat now this very fine-tuned, optimized model of domain experts without knowing anything about alloys and steels. So I'm very naive about this field, but just fine-tuning an LLM on that. And we found this to be the case across different topics, across different ways of asking questions, so for different data sets, from molecules or materials to reactions. Then for regression problems, that means going from a question to a number, the classification, as you have just seen, to go to classes like toxic, non-toxic, or even then for inverse design, that means going from desired properties of a compound to then a molecule that has those properties. And the very interesting part in here is that you are very flexible in the way that you can input data into a system. So you can basically use different representations and then still make it work very easily. But the problem there is, of course, if you now want to come back to our vision of kind of linking our recipes to the outcome, you need to have the recipes in the first place. We need to obtain enough data to then kind of train our models. And I guess this is shared by many of you, this concern, how to get your data, how to train the models, on what data can we do that? And this was a question that also a student in my team asked herself, basically how to obtain relevant data for her problem. And her problem is how to design polymers. So she's a chemist and she cares about predicting how different copolymers will self-assemble. So if you make a polymer, you react two monomers or more monomers into, we call them now just A and B. We have two balls here. And depending on how A and B like each other, how they react with each other, you can form different architectures of polymers. You can form a random copolymer where you have alternating A and B, A and B, A and B, or you can have a system where A likes to react more with itself and less with B, and then you have regions where you have mostly A and then only a few B's in there. So basically knowing how the different monomers react would allow you to basically predict what system you get out if you have a random architecture or a more blockwise architecture. And this would be important to then design optimal polymers for given applications. And of course, chemists care about this. And so they have some numbers for this. So they have the reactivity ratios that they call R to describe how reactive the monomers are. And you can then get a ratio of the R's and then this way have a heuristic telling you what you will get in the architecture. So knowing the R's basically tells you what you will get in the end as the architecture of the polymer. So the question is now, how do you get those R's? And interestingly, you have some papers where you have those R's in there, but the tables in there are typically quite ugly. So of course, the different R's depend on the conditions, like on the solvent you have in the reactivity will change with different solvents. But more importantly, most papers where you find this look like this. So this is like one of the better tables that we can still read nicely. But when Mara went through the literature, she found that most papers on this have been written before I have been born, and basically. So most of them are not even like clean PDFs with text in there, but just scans, because measuring those things is very time consuming. And it has been mostly done in like the golden age of polymers. And then later, there's less incentive now to measure those things because it's very time consuming and you have then little impact in terms of papers by doing this. So you basically have to find a way to deal with those old, very ugly tables to then basically rescue those R values from those old images. And for this, Mara tried two different routes. And if you now want to use in hackathon data from papers, this might be interesting to you, because typically people rely on going via OCR, then basically converting images into text using a model like Nougat from Facebook or Marker, and then apply an LLM on this text. But Mara also tried to directly be very bold and just use an image model. So it takes a PDF and has one image per page, and then applies a vision model on those images. And then the goal is to basically obtain from those papers then the structured output here, where you have conditions of the reaction and then those R's, the reactivity constants, that tell you how you will form the copolymer in there. And then she found what is shown here. This spot's very busy, you have many things going on here, but the important thing is to basically compare a few different groups of lines. So you show here different ways of measuring how good the system is, so how basically costly it is, how efficient it is, but most importantly, perhaps, how precise it is. And of course, in this plot, always the best outcome would be at the outer rim here. So if you are at really the outer limit of this plot, you are perfect. And then we have in here different models. And the most interesting comparison perhaps is to have the comparison between the ones with the plus in here, so plus Nougat or plus Marker, against all of the vision models here. And you find that basically, if you use kind of this conventional approach, doing first OCR and then an LLM, you have way worse performance than if you use a vision model. So vision models here perform way, way better than using the OCR approach that you would have here. So basically, if you have old papers that you just have as scans, and perhaps trying a vision model on it might be a good approach also for you. And then what Mara found is that while she had now good precision in principle, 77%, it still isn't really good enough for doing high throughput studies to train a model later on this data. So you had to find a way to improve, to boost this accuracy from like this almost 80 to something higher. And what she then did is something that I think is very creative. So she basically takes those PDFs and then asks the model to rate them on a scale how ugly those papers are. So she asks the models to tell her on a scale how crappy do the images, how crappy are the tables in this PDF, and then has a vector telling in different ways on a scale from 0 to 10 how crappy the tables are, how ugly the pages are. And then she trains a model to correlate those crappiness ratings with the likelihood of the extraction being correct. So she can then basically tell by putting a PDF into this crappiness detector how likely the extraction will then work or not. And you can then discard the ones with low probability for being extracted correctly. And then she obtains this very big boost in performance from basically around 80 to 94%. And George now has really a pipeline and also trains models now to predict copolymers by using vision models to extract data from PDFs. And if you want to learn more about this, we also have been writing a long review and also online book with examples and tutorials for different ways of doing this. We have agents in there, we have vision models in there, validations in there. And so you can have the interactive online book, but also here a tutorial on archive. But of course, if you now use some kind of LLM or vision model to extract data from papers, you would like to also know how important the model that you use in there is for performance. Because if you extract solvents or temperatures, the model should at least understand what a solvent is, and then to basically be able to link synonyms for solvents perhaps in your output. So knowing how good your model is in chemistry is somehow important to then pick the best model for the extraction pipeline. And to basically know what is best right now on the landscape of models for chemistry, we have been building with a big effort a benchmark to basically compare how well the current leading models compare to human experts. And so we have been building a corpus of questions, exam questions from university here, or other universities, and also this interactive app to then basically ask both humans and models questions about chemistry, material science, and then check how well they do. You can also test yourself if you want. And basically, we had then this big group of collaborators trying out the questions. And you see here the core team who have been pushing the piping behind all of this, because a lot of work going on in making it work reliably with parsing the LLM outputs, calling the LLMs correctly, and so on. But then importantly, we have this big corpus assembled with this core team where we cover a bunch of different areas of chemistry. So we try to be diverse in what we cover, from more safety aspects to organic chemistry to also then material science or technical chemistry. And in all of those fields, we also cover different skills, like what the model or human has to be able to do. So if it has to know some stuff, or if it has to calculate certain things, or if it has to reason or have to have intuition for solving a given task. And you can see here in those bars that we try to also have at least some sampling of the different skills in all of those categories. And then we have this big corpus assembled, and then we can basically now ask both humans and the models those questions and then see how they perform. And this is then shown here. So here we have a measure of how well we do across the entire corpus. And of course, here the best would be to be at 1. So we have all questions correct. And we then have here some of the models we tested, and one, the reasoning model from OpenAI, here at the top. And then we have different lines for the humans here. And we have here in green the average human. So those are PhD students here in Jena and also Cambridge. And then we have here the best human in our study. And so you see that the best human in here performs almost half as good as the best model in here, which is, I think, very impressive that the models are at this level. And of course, you now might argue that this tells you more about the questions and the exams than about the models. But I think in the end, if we now have models that perform on exams we use to test also humans way better than those humans, at least we should think about how we now test humans in the future. And also, I think if I would now have a student walking around the hallway in my university that performs, that aces all the exams that well here, that is better than the best PhD student here, I would probably try to find ways to use those students in also my research in my lab. And so I think basically we're thinking how we educate and we're thinking how we then leverage those models is very important. But crucially, it also depends a lot on what topics we test the models on. So here we have, again, a complex plot showing our performance across different groups of questions, different topics here. And again, the best performance would be at the outer rim here. And then we have in colors here different models. And again, O1 here in this color. So it's the best one on most topics. And we have the humans here in the middle. But you see that for some topics, especially if you have to go from a text of a compound to a reasoning about a compound, the models perform quite badly. So here, for instance, in analytical chemistry, we have relatively low performance still. And this is mostly because of questions where we ask the model to predict, for instance, for a given smile strings or text for a compound, how many peaks it would have in an NMR spectrum for this compound. And for humans, this would be easy because they just have to see how many protons do they have that are symmetry equivalent. But a model has to go from text to a 2 or 3D representation of this compound and then reason about the symmetry of the protons in there. And this right now somehow still is very hard for models to do. And thus, if you just rely on textbook-like questions, they're basically outperforming all we have here. But if you have to go through reasoning about symmetry or spatial structures, they still struggle a lot, those models. And then you might say, of course, then I want to not trust those models, and you don't have to, luckily, because you can use them with tools. And this here, one example of what you could do, you could basically then build a system where you can have an interface where you can ask questions about chemistry, and then the models would just call different tools, simulation engines, databases, Python code, and then using those tools give you answers. So the models wouldn't just answer it by themselves, but they would instead build a workflow calling the right tools in the right order and just develop the right inputs and the right outputs for calling the tools. And if you would like to know how to build those tools, there's a tutorial how to build them from scratch with just plain Python code and without fancy frameworks on my blog, on my website. But in the end, it's a very reliable way to really see what happened, and you have in the end then no longer a black box, but a white box, because you can really know how and why you obtained a certain answer in it. And one thing I think they will be really important for is for the mentioned lab notebooks. So if you develop those lab notebooks are a big pain in the ass because users tell you, I want to have this field here, gonna want to have something else in here, want to have this or that, and they want to have all their custom personalized way of how this ELN should look like for them. But of course, if you develop this, you cannot customize every ELN for every user. You have to develop like one system, and then you have to make compromises. But I think now with those models, you can have a really personalized and customized ways of giving users ways to query the data in a very personalized and interactive way. So you can now just interface with the data within an EL and then let the users chat and interact directly with the data in the EL and then dynamically let them customize the way they want to play with data as they want on the fly and without coding it up yourself, but letting users then do it for themselves. And I think this is a very promising way forward. And thus, we also think more and more about how to deal with the stuff that we have in those ELNs. And of course, we have the things that go beyond just text. So we also have images in there, we have structures in there, spectra in there. And right now, we have for all those different, we call modalities, different models. And we have a model that deals with graphs, a model that deals with NMR spectra, a model that deals with mass spectra, and they don't speak to each other. So that basically we just have islands right now with different models. And also if you have to search for something, you just search for this one thing, but you have no way to search across different things, to search for images using text or for text using images, for instance. But in the end, if you could now put into your lab notebook the measured mass spectrum and obtain the matching recipes or the matching compounds, it would be really a game changer because you could now do very more flexible ways of how you can actually do chemistry. And so Adrian's goal here was to build in those links here to basically let the different domains, the different modalities speak to each other to basically now make a multimodal system where you can now put in a measured procedure or measured spectrum and then find the matching other modality very easily. And for this, he has a very interesting way of training the model. So he trains only on those black lines here. So he basically does some contrastive training, aligning embeddings here, and then gets the blue links here for free without directly training on them. And the first thing he tried was to basically convert spectra to structure. So he inputs now measured spectra, mass spec, NMR, and IR, and you can then basically put in 2, 3, 1, whatever you have, and then you want to obtain the corresponding structures that you have in those spectra. And for this, he has first a retrieval stage. So he has now aligned embedding vectors. So each spectrum will be a vector. And he has a database of compounds, and they also are vectors. And then he has them aligned with contrastive learning and can now find by comparing vectors which spectra, which are closest to which compounds. So he basically can measure how similar different spectra with different compounds. And you can just also add more and more spectra because it's a very flexible training framework. And then you can find out basically by combining different spectra very easily what he has. So you can now retrieve stuff efficiently from databases. So you can basically put in IR and find then in 70% of the cases the right compound, or then add IR plus NMR or different NMRs plus IR, and then find almost all the right compounds by just looking up in this aligned vector space. And so basically, if you now see the output would be a ranked list of compounds, and if you have now more than one modality, you basically have the right compounds almost always within the top 4 entries of this ranked output list by just measuring how close stuff is in the shared vector space. And luckily, chemists are creative, and so the compounds they deal with won't be always in a database. So this here right now, it seems that you have stuff to look for in a database, but if you don't have this compound already in a database, you will be out of luck. So if you make something new and you don't know what you made, you are out of luck with this approach. And thus, he also has a second stage where he takes now the best outcomes from this retrieval part and then evolves the molecules to best match the compound. So he basically modifies the structure to then best match the spectra, and then has a ranked list of compounds where some of them are retrieved and some of them are new. You can in this way very much contextualize the outcome and also predict stuff that you haven't measured before, but still have then in the end the best match between spectrum and structures by having the multimodal alignment. And you see here, this works very well. So we have here how often you have the right novel compound by running this GA. And we have here a model trained to translate directly from IBM spectra to structures. And we are way better than that. And so you have the right compound in more than 85% of the time, even if it's a novel one. So even if it's not in a database, we evolve the compounds to the right spectrum quite frequently. And interestingly, you can also in this way find mistakes. So if you now have a compound in your ELN, you then perhaps want to see if you put in the right spectrum for this compound. And since we now can compare everything in this unified vector space, we can match how close your compound is to your spectrum. And then Artin went into literature and looked for cases where the spectrum doesn't match the compound. And there has been a bunch of cases where this happened. So here you had initially this compound here assigned, but then people later found actually that they measured this compound for a given NMR spectrum. And so basically Adrian can now reliably detect with this low score here. And so basically if a score is below 0.8, it's a very unreliable match, that those matches they find initially are very unreliable, but then also evolve using his algorithm them to the right structure. So basically, if you now input a first guess plus your spectra, he can now evolve this to the correct structures. And so this way, have a very convenient tool for chemists by basically aligning different modalities in a shared vector space. And I'm coming now to my end, so skip some parts to let you also some time for a break. But this is something we also push currently in Helmholtz in a big initiative. with 20 millions by the association to build also a model for photovoltaics, where you do the same thing more or less for then PV modalities like device stacks, images, SEM images, JV curves to then have different downstream tasks on different modalities. One thing that might still be important to you is multimodal models and how well they do. And typically you would like to have in your life cycle of doing science, you go from extraction data, like finding data in papers, running experiments, and then like checking your results. And so we have been building with Navav, Martino, and also folks at an IT Daily a benchmark to basically measure the full life cycle of science in a lab or also in silico experiments, and then test the different models, how they can help us assist, how they can assist us in the different steps of doing science in this life cycle. And there, compared to just the text model, so this is now here multimodal benchmark with the images of the lab, like what is unsafe in this image, for instance, here, you have way more variance, and you have basically models performing quite differently for different tasks. And so if you want to use the vision models, it's way more shaky than with the text models. But more importantly, so if you have the choice of going between image and text, so if you can express the same information as text, right now going with text is better for you. And also if you can right now express your thing with just one reasoning step instead of multiple ones, go with just one reasoning step. And also they're still like very fragile, and there's a strong correlation between performance and how often you have the structures based in the internet. But with this, I want to basically kind of close. I think we have now made a lot of progress in kind of using LLMs in different ways to capture data, to then drive entire systems using our agents, but then to also predict things and come up with new compounds. And I think we can use the many different parts of this accelerated science workflow where we can really drive in our experiments using agents, mine data, and in this way autonomously at least run certain parts of the research workflow. And I want to thank my group, but also if you want to join my group, I'm hiring on levels, so let me know. And also the funding agencies, of course, that have paid for this work, but also my work at EPFL, of course. And hopefully we can together with those agents and some of you push forward what we can do for material science and chemistry, and hopefully discover new powerful compounds using those systems. And thank you for your attention.